Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Calculus series and concerns the differential operator. This guide introduces differentiation of a function by application of the differential operator. It then shows how this operator can be used to differentiate more complicated functions of x. Introduction. The idea of an operator in mathematics is extremely useful. You can think of an operator as a piece of mathematics that does something to a function. Importantly, operators can describe processes in mathematics that cannot be described as functions. One of the first examples of an operator you come across is differentiate with respect to some variable, for example x, which is called the differential operator. The differential operator with respect to x is written as either d by dx or d subscript x. When you use an operator, you are said to apply it. For instance, if you apply the differential operator to a function of x, you are said to be operating on the function of x. You still use the familiar rules of differentiation to find the derivative. However, when you apply an operator, the concept of differentiation is presented in a different way. You can read the study guides, Differentiating y equals ax to the power n, Differentiating basic functions, the chain rule, the product rule, and the quotient rule, if you need help finding derivatives. You can also apply the differential operator to other variables such as y, if they are a function of x. Doing so gives some notation that you are probably already familiar with. d by dx of y equals dy by dx, when y is a function of x. For simplicity, this guide only talks about differentiation with respect to x, but the notation and methods discussed are the same for other variables. Example: apply the differential operator to the expression 5x to the power 4. When you apply the differential operator to an expression such as 5x to the 4, you write d by dx of 5x to the 4. The result is the derivative of 5x to the 4 with respect to x. This is found by using the power rule of differentiation, and so d by dx of 5x to the 4 equals 20x cubed. Example: apply the differential operator to the equation y equals 5x to the 4. To do this, you apply the operator to both sides of the equal sign and write d by dx of y equals d by dx of 5x to the power 4. Here, the brackets are used to imply the application of the operator, not multiplication. So the left-hand side shows that the operator has been applied to y, resulting in the derivative of y with respect to x. Combining this with the result from the previous example gives dy by dx equals 20x cubed, which is the same result you would get by direct application of the power rule. Example: apply the differential operator twice to y equals 5x to the 4. The previous example shows that after one application of the differential operator, you get dy by dx equals 20x to the power 3. Applying the operator to both sides of this result gives d by dx of dy by dx equals d by dx of 20x cubed. The left-hand side is the second derivative of y with respect to x, which is written as d by dx of dy by dx equals d2y divided by dx squared. This is the second derivative as two applications of the differential operator. The notation used to write the second derivative should make more sense when seen as a result of applying the differential operator twice on y. Returning to the question, the right-hand side can be found by using the power rule. d by dx of 20x cubed equals 60x squared. Combining these results gives the second derivative of y equals 5x to the 4. d2y over dx squared equals 60x squared. The differential operator and more complicated functions. The study guide, More Complicated Functions, explains that you can combine basic functions, power, sine, cosine, exponential and natural logarithm, in a variety of ways to make more complicated functions. If y is a function of x, then you can extend this idea to include y and functions of y too, as they will be composite functions of x. You can use the differential operator to differentiate these kinds of functions. If y is not a function of x, you need partial differentiation to perform differentiation. See study guide, Basics of Partial Differentiation. The following discussion assumes that y is a function of x. Addition and subtraction. Applying the differential operator to more complicated functions made by addition and subtraction of basic functions is performed in the same way as for conventional functions, using term by term differentiation. Example: apply the differential operator to y plus 7x cubed equals 5x to the 4 plus 6x. Usually you would rearrange this function for y and then differentiate it. However, you can apply the differential operator to both sides instead. d by dx of y plus 7x cubed equals d by dx of 5x to the 4 plus 6x. You apply the operator to each term in turn on each side. d by dx of y plus d by dx of 7x cubed equals d by dx of 5x to the 4 plus d by dx of 6x. The first term is the derivative of y with respect to x, and the other terms can be found using the power rule, and so d by dy plus 21x squared equals 20x cubed plus 6. You can rearrange the result to find the derivative of y with respect to x. dy by dx equals 20x cubed minus 21x squared plus 6. Multiplication and division. Including y in the way to make more complicated functions means that you can use multiplication to make expressions such as xy or y times e to the x. A very useful aspect of using the differential operator is that you can apply it to these types of expressions, which are not covered by basic rules of differentiation. However, because y is a function of x, you can still use the product rule to perform the differentiation. Example: apply the differential operator to the expression xy. To do this, notice that the term is the product of x and y is a function of x, so you use the product rule in combination with the differential operator. d by dx of xy equals x multiplied by d by dx of y plus y multiplied by d by dx of x, which equals x multiplied by dy by dx plus y multiplied by 1, which is simply y. The method is similar if you have an expression that can be differentiated using the quotient rule too. Composition. Here, as y is a function of x, if you apply another operation to y, for example to give y squared, sine y and so on, the result is a composite function of x. Therefore, when you apply the differential operator, you are differentiating a composite function, and so you need to use the chain rule. You can use the chain rule to rewrite the differential operator as d by dx equals dy by dx multiplied by d by dy, differential operator form of the chain rule. Significantly, you have changed the operator from one that differentiates with respect to x on the left to one that differentiates with respect to y and multiplies by dy by dx on the right. Use the dy by dx multiplied by d by dy form of the differential operator to differentiate composite functions of x that are expressed as a function of y. Example: apply the differential operator to y squared. As y squared is a composite function of x, you need to use the differential operator form of the chain rule to perform the differentiation. D by dx of y squared equals dy by dx multiplied by d by dy of y squared, which equals 2y multiplied by dy by dx. You can use the differential operator to differentiate the 5 basic functions as shown in the following table. If the function of y is a times y to the power n, its derivative is an multiplied by y to the power n minus 1 multiplied by dy by dx. If the function of y is a multiplied by sine ky, its derivative is ak cos ky multiplied by dy by dx. If the function of y is a cos ky, its derivative is minus ak sine ky multiplied by dy by dx. If the function is a multiplied by e to the ky, its derivative is ak e to the ky multiplied by dy by dx. If the function is a multiplied by the log of ky, its derivative is a divided by y multiplied by dy by dx. You can see that the derivatives follow a similar pattern to those of the basic functions of x, but due to the application of the chain rule form of the differential operator, you get multiplication by dy by dx too. Example: apply the differential operator to the expression 3y squared plus 7e to the y plus x squared sine y. Let's approach this question one term at a time. Applying the differential operator to the first term gives d by dx of 3y cubed. As y is cubed, this is a composite function of x, and so you use the chain rule form of the differential operator. D by dx of 3y cubed equals dy by dx multiplied by d by dy of 3y cubed, which equals 9y squared multiplied by dy by dx. In the second term, y is part of the exponential function, and so you use the chain rule form of the differential operator again. D by dx of 7e to the y equals dy by dx multiplied by d by dy of 7e to the y, which equals 7e to the y multiplied by dy by dx. The final term is a product of x squared and sine y. The latter is itself a composite function of x, and so you use the product rule in conjunction with the chain rule form of the differential operator. D by dx of x squared multiplied by sine y equals sine y multiplied by d by dx of x squared plus x squared multiplied by dy by dx multiplied by d by dy of sine y, which equals 2x sine y plus x squared cos y multiplied by dy by dx. Combining these results gives d by dx of 3y cubed plus 7e to the y plus x squared sine y equals 9y squared times dy by dx plus 7e to the y times dy by dx plus 2x sine y plus x squared cos y multiplied by dy by dx. You may notice that there are two types of terms in this result, those which are multiplied by dy by dx and those which are not. You could write d by dx of 3y squared plus 7e to the y plus x squared sine y equals 9y squared plus 7e to the y plus x squared cos y, all multiplied by dy by dx, plus 2x sine y. This type of factorisation is common in implicit differentiation. See study guide, Implicit Differentiation. Further guidance and information. If you have any further questions about calculus or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of calculus, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.